So this is part 3 of the video series on Newman projections. In this video, we're going to go through a conformational analysis of ethane, propane, and butane. This is a really common homework question that people will get in organic chemistry. And so you can use this to kind of help guide your answers. The one thing that I do want to caution you about is that this energy table is sometimes given in different units. So just make sure that you're using the appropriate units as you're filling out your diagrams. All right, so let's start off with ethane. So ethane has those 2 carbons, propene has those 3, and I put red dots on the structures to kind of help guide you. And then butane has 4. So that's the key difference between the structures across ethane, propene, and butane. But if we start with ethane, we can see that both of those 2 carbons only have hydrogens on there. And so I already filled out this first Newman projection here, but we can see that we really only have hydrogens on the entire molecule. And when we rotate around that back carbon, we really just get that those hydrogens in the back shift over, and there really isn't a difference across any of these Newman projections at the different rotations. And again, that's because we just have those hydrogens, not really a lot changing as we rotate the bonds. However, what we do see is that we do have a shift. As we rotate, we go from that staggered state to an eclipsed state. And so the energies between the 2 states are going to be different. And so to determine what the total energy contributions are to these different states, we first have to identify the types of interactions that we have. And so for the staggered state, we really only have hydrogen-hydrogen gauche interactions. And if we take a look at our table up here, we can see that hydrogen-hydrogen gauche interactions have an associated energy of 0 or negative contributions to the stability of 0. And that's because in the gauche state, we don't have any torsional strain. And we also don't have steric strain between hydrogens because they're too small. They're too small of groups to actually come close together and have any sort of steric strain. And so based off that, we really don't have any contributions to the energy. And so we're going to have a 0 energy associated with that staggered state. The same is true for these 2 other staggered states where we still only have those HH gauche interactions. And so for those 2 states, we can also put 0 here. Next, we can take a look at the eclipse states. And so in these, we can see that we end up having multiple eclipsed interactions between the hydrogens. Each of these eclipse states has 3 hydrogen-hydrogen eclipse states. And each of those is going to contribute 4 based off of this table over here. And so we have contribution of +4, +4, +4, and so a total of +12. And same thing is true for these other 2 eclipse states where both of those end up with +12. So if we go back to our diagram, we could indicate that the +12 state is somewhere over here. And at 60 degrees, at 180 degrees, and at 300, we're going to, all of those are going to have the same +12 energy. And then to fill out the diagram, we would just use that wavy pattern to fill it out. And then if you have to draw that diagram going down to 360, that 360 state should just be equal to 0. So it'll go back down to baseline if we continue it to along the x-axis. All right, so ethane's pretty straightforward. It's just that wavy pattern where all the peaks are equal and all the bases are equal. So let's move on to propane. And so in propane, we now have the addition of this methyl group right here on that back carbon. And so to fill out all of our Newman projections, that front carbon would stay the same with those hydrogens, and we would just rotate that methyl group clockwise by 60 degrees. And we should end up with something like this as we fill in all of those Newman projections. And we can see that the main difference is that that methyl group is kind of just making its way around the circle. All right, so now to calculate the energies, it's not going to be as straightforward as that previous question, just because we now have that methyl group. It's not just hydrogens. And so the types of interactions that we have here in this first one are going to be a methyl hydrogen gauche. And then we also have a hydrogen gauche. And so if we go back to our table, we can see that the methyl hydrogen gauche also ends up being 0, along with the HH gauche. And so we have a total contribution of 0 for those gauche interactions. However, we should always just double check that. The reason it's 0 is because that hydrogen is too small, so it doesn't contribute to that steric strain. But there are groups that can have gauche contributions. All right. So since neither methyl hydrogen nor hydrogen gauche interactions contribute energy, those staggered states are going to be +0. And we can just automatically do +0 for all the other staggered states, since those have the same types of interactions there too. All right, next we can take a look at the eclipse states. And so here we have 2 different types of interactions. We have these hydrogen eclipse states, which from the table we know is +4. And then we also have a hydrogen methyl interaction, which is different from that previous example with ethane. And so for hydrogen methyl, we have a +6 eclipsed contribution. And so when we calculate our total, we would end up having +14. And then if we look at the other eclipse states, we end up having those same interactions where it's 2 +4s and 1 +6. And that's because as we move that methyl around the circle, we can only have it be eclipsed with another hydrogen. So there's not really a lot of differences between the different eclipse states. And so altogether, we can do that +14 up here. And here my energy diagram is actually a little bit skewed from that previous one. Can make it a little bit taller so that we can see a difference between this one and that previous one. All right, and so now we can fill in that wavy pattern. And similar to that previous one, if we continue down to 360, we would end up matching with the 0 state. I'm going to redraw that just because one of the states was a little bit imperfect up here. All right, so again, in this one, all the peaks are the same because the states are equivalent, even though it's different hydrogens that the methyls interact or eclipsing with, and the bases are all still going to be 0. However, we can see that the peak is a little bit higher than in the previous one. In the previous one, we had +12. Here we have +14, indicating that that rotational barrier is higher for propane in comparison to ethane. All right, finally, we can do this last one. And so for this one, we have 2 methyl groups on each of the carbons. And so when we rotate, we'll keep that front carbon the same. And what we'll do is rotate that back carbon. So this methyl group in the back ends up eclipsing with that hydrogen first. And we could just make our way around to fill in the rest of them. And again, the easiest way to do these is just to keep that front carbon stable and then rotate the back carbon. But you could also rotate the front carbon. You should get this overall same graph. You might just have different angles that correspond to the different states. Okay. All right, so now we have our Newman projections for this one. And so now we have to calculate the energies. And we can start with this first one. And so in this first one, we have methyl hydrogen gauche interactions. between the two methyl groups and the hydrogens that are surrounding it. And so from that previous part, we also know that all of those are +0. And so the total for this one is going to be 0, similar to the previous ones. Oops, I switched over to those practice questions. So we're going to start off with 0 for that first one. And this one is 0 because those methyl groups are opposite each other. They're not next to each other, so there's no interactions that we would have to consider for methyl-methyl. All right, next, in this next one, we can take a look. We have 2 hydrogen methyl interactions, each of which is +6. And then we have a hydrogen-hydrogen interaction, which is +4. And so for this one, we have a total of +16. So I'm going to change my y-axis again, just to make it a little bit taller. And so we'll have +16 here. Next, we can take a look at this 120 degrees. And so now here we notice that we have this methyl and methyl next to each other in a gauche interaction. And now these methyl groups are big enough to experience steric strain. And so we have a small contribution to the energy based off that gauche interaction between methyl-methyl, which is going to be +3.8. And so this is a different interaction than we've seen in the previous molecules. And that's because now we have bigger groups that are actually capable or big enough to experience steric strain. And so here we'll see that we have a +3.8 energy contribution in this interaction. And then all the other interactions in this molecule or in this structure are going to be 0 because we know that hydrogens don't have those gauche contributions. All right, next we can do this this next one. So here we have 2 hydrogen-hydrogen interactions, each of which is +4. And then now we also have this methyl-methyl interaction, which based off the table in the eclipsed state has a 11 contribution. And so the total for this one is going to be +19. Which is going to be higher than that previous state of +16. All right, so now we have +19 here. In this next one, you can see that this is very similar to that 120, where we still just have that gauche methyl-methyl, and that's going to be +3.8, and so it's going to line up with 120. And then lastly, we can do this eclipsing one. We have plus hydrogen-hydrogen, which is +4. Then we have hydrogen methyl and another hydrogen methyl, each of which is +6. And so this matches the 60-degree rotation one. So this one's going to be a total of +16. And so that will match 60 degrees. All right, next we can fill in that wavy pattern. And what we notice here is that the worst state or the highest energy is this one. And so a very common question on homework assignments is to label the least stable conformer. And so that's going to be the one with the highest energy. You could also be asked to label the most stable or lowest energy, which is going to be at 0 degrees, where those methyl groups are anti to each other. All right, and so the key difference between butane, or this last one that we're doing in comparison to these other two, is that we can see that the eclipsed states are not all equal. The eclipsed states where those methyl groups are eclipsed instead of methyls with hydrogens is much worse for the stability than the eclipsed states where it's the hydrogens overlapping with the methyls. And we can also see that the staggered conformations are also not equivalent. in that there is a small energetic penalty to having the methyl groups closer together within the molecule. All right, so that wraps up the conformational analysis of these three molecules. If you haven't done so already, I recommend going through these Newman projection practice problems, and there should be a video posted with the solutions for those as well.